we'll log back in hopefully here real soon. I didn't mean to disconnect everybody. I told it leave meeting, but don't end the meeting. But for some reason, I guess it kicked people off. Anyway, we're back. So let me, we had Levi and I think Miranda were also with us before. Let's see, this is, I'm going to run down the hall and put my cat in a different room so she won't bother us, okay? So hang on. Okay. Well, I don't see anybody else yet. It's the same meeting. It's the same link that I sent out. So hopefully they'll go back to their email and click on the link again. Okay, well, I'll go ahead and start. If they come on, maybe I'll repeat some of this, but we'll go ahead and do some now. So one thing I wanted to talk about was this idea of p-value. Okay, that's an important thing in statistics, and I want to explain to you what the p-value is, what it means. Okay, so this p does come from or it does stand for probability, okay? But we call it a p-value because there's different probabilities, and it gets its own special name. So when you're doing, here's the general idea, Olivia. When you're doing a test, and a hypothesis test, okay? And there's three different versions of a hypothesis test. I'll write that down here. It's another point. I was thinking about doing a separate thing on it, but there are three different hypothesis tests. Okay. There's a two-tailed test, and then there's a one-tailed test, okay? But the one-tailed test splits into, so up here for two-tailed tests, I'm going to write mu sub naught. So mu sub naught is the mean value for your null hypothesis, okay? So up here, we always have HO. We always have the null hypothesis, H sub 0 or H sub O. We always say mu equals, and then we'll have some value here, some number, right? And then I like to write a little O here next to this, and you'll see that in some of the literature sometimes. Mu sub naught. So this means this is the null hypothesis. It's the null mean, okay? So there's three different statistical tests, but they all start with HO mu naught equals something. No matter which test you've got, this first statement is the same. Your null hypothesis, you're just stating what the claimed or status quo value is for the population mean, or we could be, okay, hypothesis testing also can be broken down into a couple different categories. And like what I'm saying is we can either be doing means hypothesis testing or proportions hypothesis testing. So if we were doing means hypothesis testing, this would be mu sub naught, or the population mean. But we could be doing a test on proportions, right? And then it would just be, it's the same. You would have HO. If it was proportions, you would have HO, and then you would put P, which is the population proportion. And again, I would put a little 0 there, P naught. So we know that's the null hypothesis proportion. And same thing, it equals a value, okay? So two different versions of hypothesis testing. There's proportions and means, okay? And so if you're doing proportions, this is always the null hypothesis. You just state, you write down HO, that is the null statement, and you write down the value for the population proportion. If you're doing means testing, HO, the null hypothesis statement is that the mean for the population, and we call this the null mean, or the mean for the null hypothesis, is equal to and a value, okay? And so for each one of these, there's 3 different possible alternative hypotheses, okay? In the so HA, this is your alternative hypothesis, okay? So hypothesis testing is always a pair. It's so all hypothesis testing is a pair of statements. You have HO and your population parameter. I'll put that population parameter. So in means testing, this would be a mu, and oh, you can't see that. In means testing, this would be a mu. In proportion testing, this would be a proportion. But so all hypothesis testing, you have a statement, the null hypothesis is HO, some parameter equals some value. And then you have HA, which is the alternative hypothesis, okay? And so all hypothesis testing is a pair of statements, okay? It's these 2 statements. Now, so there's 3 different kinds of hypothesis tests. There's a two-tailed test. So on the two-tailed test, HA, which is the alternative hypothesis, you say the population parameter, and here I'll use means, but we could be dealing with proportions too. But the null mean is not equal to the value that we listed up here. So in the null hypothesis is always a statement that the null mean is equal to some value. The alternative hypothesis, if we're doing a two-tailed test, is alternative hypothesis is mu sub naught population mean is not equal to the value, okay? That's a two-tailed test. But we could be doing a one-tailed test, and there's two versions, right? One is mu sub naught is greater than the value. And the other version of the one-tailed test is mu sub naught is less than the value. Okay, so that's a good summary for all the hypothesis testing we would do. And in this class, there may have been one problem. I'm trying to remember. There may have only been one problem in the whole set that was a one-tailed test. So most of ours have been two-tailed. But the key is you look at, so this is, let me write out here, this is HA, okay? So what differentiates these tests is always just the alternative hypothesis, because the null hypothesis is the same no matter what kind of test you're doing. It's a statement that the parameter is equal to a value. So that'll help you on a lot of those problems. But the alternative hypothesis, if you're saying it's not equal to a value, that's a two-tailed test. And so that's one possibility. Or you could have a one-tailed test. Looks like a K there. You could have a one-tailed test. And the alternative could be that mu naught is bigger than that value. Or you could be doing a different one-tailed test. And you could be saying mu naught is less than the value. So these are two different tests, right? So altogether, there's three possibilities. Okay, so let's get back this business about p-value. So here's let's look at a two-tailed test. Okay, so on a two-tailed test, we know it's two-tailed because we say HA mu naught not equal to this value, okay? So this is the key here. This is what tells us it's two-tailed when we have not equal. So the problems we're doing in our homeworks, they're all word problems, right? And so you just have to carefully read it and see what is it asking. And a lot of times they'll say test at such and such significance level, because you always have to know what significance level, which is this another way of saying what confidence level you're testing at, okay? You always have to know that, because your results, that's part of the report of your results. You have a certain result based on a certain significance level or a certain confidence level. You can't give a result without stating the confidence level it was tested at, okay? What was the point I was going to make there? So the test is, for a two-tailed test, okay, so what we do is we propose that there's this distribution that if it's a z-curve, it is a normal distribution. If it's a t-curve, it's like a normal, it's close to it, okay? So this could be a t or a z-curve. There's only one z-curve, only one, all right? There are many t-curves. They have slightly different shapes, and it just depends on what your degree of freedom is, specifies which t-curve you're talking about, okay? But when you draw it, you just draw out this normal bell-shaped thing every time. So this value over here that we're talking about in our hypothesis test is always the center value here. So this is what you're proposing, or this is what the claim is, right? The status quo or the published value, or somebody says in known research, here's the value for this population, right? And when we do a hypothesis test, what we're doing is we're testing, does our data agree with that this is the value, because this would be a scale in X, say, right? So we have some value of X. that we say occurs at the center. And then we know this value is also 0 if we're talking about a statistic, whether it's t or z, the center point 0, and then you've got standard error units, right? Which is the standard deviation of either x bar if you're talking about means, or it's the standard deviation of p hat if you're talking about proportions. But anyway, when you're doing a test, this is a proposed value, or this is the value you're testing, okay, the claimed value. And then we're going to do a statistical test. And here's what you do is you have to state your hypothesis. So that means you have to, so you say HO mu naught equals some value, right? Whatever that value is. And then you have to state what your alternative hypothesis is. So here we're going to say mu naught is not equal to the value. So this tells us it's a two-tailed test, okay? So what's the next step here? To determine confidence level of the test. That you wish to use, okay? And sometimes you're given this. Sometimes maybe if you're working, somebody will say, hey, we need to run a test at such and such a confidence level, okay? And remember, when we say significance level, this is another way of saying the same thing. So you can use either one of these to communicate the confidence level or significance level that you're talking about, okay? And remember, it's 1 minus the confidence level equals the significance level. So if we're testing at 95% confidence, that's a probability of 0.95. So you could write probability here. So, because you could talk about this and say our confidence level is 0.95, that means that's the probability. Or you could say it's 95%, right? You're talking about the same thing in either case. But if this is a 95% confidence level, the significance level is 0.05. It's 1 minus this, right? So we're doing our test. We state what HO is, what the value is that mu is supposed to equal. Then we're going to test that. We're going to go get a sample and see, and from our sample, we calculate a statistic, and the statistic is going to tell us which one of these hypotheses that we're going to go with, right? And so the outcome of the test, okay, is just you're either going to reject the null hypothesis, or you will not reject the null. So this is what you're doing when you conduct a statistical test, and there are many different kinds, but you're always doing the same thing. You've stated what the null is, and you have to state which alternative you're talking about. And because we said it's not equal to the value, that tells us we're doing a two-tailed test. Okay. We have to determine what confidence level or significance level. It's two different ways of talking about the same thing that we're testing at. usually it's 95%, which makes the significance level 0.05, but it doesn't have to be. You could test at 90% confidence. You could test at 99% confidence. Okay, but most of our problems, it's 95, okay? So once we determine here's why we have to determine the confidence level of the test, okay? We're gonna get a thing, and I'm gonna say we're using the Z statistic, okay? And I think I've talked before about, in some cases you use Z and in some cases you use T. All right, but let's say we're using the T just for this discussion, but the same thing's true for the T. It all works the same way, okay? So we have a Z star value, and that's actually this point. That's where on this x-axis this point landed, okay? Because remember, if this is an X scale, then there's also some, down here, there's a Z value that corresponds with this X value has some Z value. And what is Z? It's a count of how many standard errors you are away from this center value. That's what Z score is. I put Z score. You've heard that word score. Sometimes they just write Z, is a count of how many standard errors we are, hopefully that's not too small to read, we are away from the mean, okay? And this is true whether you're talking about means testing or proportions. If you're talking about proportions, then this value would be P naught. It would be the population proportion. But Z or T is just a count of how many standard errors you are away from this value. And when I say you are away from, what I'm talking about is your sample, okay? But before we get a sample, so this is before the sample, okay? We get this number, and this number is determined just from this. Whatever the confidence level is determines what the value of Z star is. That's why we have to know what the confidence level is. So this Z star, we've got a mirror image thing here. So we have a minus a Z star on the other side, and that's this point. That's the Z value for this point on the axis, okay? So these are called critical Z or Z star. And I like the word threshold, okay? Because this is like our trigger value. This is what we're going to compare our sample against, this number, threshold value, threshold. So this determines what your test is. So this will be some number, okay? Now, if we're testing at a 95% confidence level, this Z star will be 1.96. Always, okay? So your confidence level determines what this number is, and it's 1.96. So this would be minus 1.96. So that says we're 1.96 standard errors away from the center. That's what the threshold value is, the Z star. And it's the same thing if you're doing a t-test. This is T star instead of Z star. But the confidence level, okay, when you're doing a t-test, you need the confidence level, but you also have to know the degrees of freedom, because the degrees of freedom determines which t-curve you're using. So the t-test, you get your degrees of freedom, and that defines which curve is being used, okay? which for our purposes, you just draw something that looks kind of like a normal curve. But if it's a t-test, this would be a t-distribution, and it comes from your degrees of freedom. And then it's just like z, okay? So you would get your confidence level, and that would tell you what the t star value would be. And you either look this up, okay, in a table. You can look up z star in a table. You can look up t star in a table, or you can get it from a computer, from Stat Lab, or you could get it from your calculator. And I put a thing on Blackboard about how to do t star in your calculator. And we've done this several times, but maybe we'll do it again. Anyway, I'm showing you just the general idea for a statistical test. So we've stated a hypothesis. So we're testing to see, is this really believable? Is this value, the claimed value, believable based on what we get for our sample? So that's the test. We go get a sample. We're going to compare our sample results with this value and then statistically say whether we're going to reject that the real value for the population mean is here, whether we're going to reject that and say, no, we don't believe that, or whether we're not going to reject it. That's what the test is. So we've determined z star from StatCrunch or from a table or from our calculator. And again, this just depends on the confidence level. So if I have a 99% confidence level, this z star would move out here, okay? If I have a 90% confidence level, I'm going to have a smaller z star. So this is just a function of your confidence level, or what is the same thing, effectively, your significance level, okay? But anyway, once we have identified these points, we go get a sample. So 3, obtain a sample, and that's a random, random independent sample. Dependent sample. Okay. And that, the sample is going to give us X bar, right? And here we're talking about means in this problem. We're looking at means and not proportions, okay? So the sample gives us X bar. If it was proportions, the sample would give us P hat, okay? So if we were doing proportions, we would get P hat from the sample. But for means, we get X bar. Well, then we convert this X bar value into its z-score. Okay, and this is called the test statistic. So what we've done here is we've go get a sample, and let's say our sample hit right here, okay? Let's say this point's where our sample hit. That's our X bar. So this is an X scale here. Our X bar value was right here. Well, this X bar has a z-score associated with it, right? This other scale, which is also goes along here. So we're just wanting to know, for this X bar, what is the z-score? What's the value of z? How many standard errors away from this mean are we? And so we get a number for that, okay? And now I might need another piece of paper. I guess I do. So redraw it here. We're doing our test. We're doing a two-tailed test. So that means there's a tail on either side. So that means we have a z-star and we have a negative z-star because it's a two-tailed test. Okay. And we got our sample, all right? So our random sample hit here. Okay, well, from this picture, we could be finished just from this picture. The idea of these tests is if your sample falls outside or past your critical statistic. So this, remember, is our threshold, right? This tells us at 95% confidence, this is the number for Z. So if we get anything bigger than that, if we get out here, we're going to reject the null that says that mu naught equals whatever value this is that we said it was in the null hypothesis, right? And it's a two-tailed test. So if we would get a sample that hit out here on the other side of negative Z star, same thing, we're going to reject it. So all we're doing is we're saying at 95% confidence, if we randomly get a sample, will be the probability is a 95% chance that our sample Z, okay, that negative Z star is less than or equal to Z is less than or equal to Z star. Okay, so this is what we're doing in the test. We're saying there's a 95% chance if you get a random sample that it'll hit from here to here, if this is the true value, if this null hypothesis that we stated is true. Okay, so if our sample lands out here, that's a low probability event. That's a rare event. If this is true, it's going to be very rare that you get something that's this extreme, that's this far away from the mean, okay? So you're going to reject the null. So the tails are the rejection region. Okay, if you get something in the tails, you reject the null hypothesis. And who says what the tail is or where the tail is? This does. This tells you at what point we're going to start counting at. We're going to count everything after this is in the tail. And we're going to count everything below this one as in a tail. So that's what this statistical test is. So you're comparing your test statistic, which is Z, with Z star. That's what the test is, okay? And if you were doing a t-test, it's the same thing. It's no different. It's just your test statistic will be a t-value, but you'll have a t-star that you're comparing it against. And that's all these tests are, okay? So that's one way of doing the test, is just if you know what Z star is, which you will know, and you get that from knowing what your confidence level was. So you have your confidence level, you just look it up in a book. If it's 95% confidence, we know this is going to be 1.96. So this is negative 1.96. So that's 1.96 standard errors away from the mean. Then Z is called our test statistic because it comes, okay, it's called a statistic because it comes from the sample, okay? Z comes from the sample. Z star is just it's our criteria that we're going to use to compare it against. And this is determined just from what confidence level we wish to test at. What confidence level we are testing at determines Z star. It also determines T star, okay, but for T star, you also need to know the degrees of freedom to get the number for T star. So for T statistics, you have to know the number of degrees of freedom and the confidence level, and then you can look up in a table or use your calculator or computer and get T star. For Z, all you need is the confidence level because there's only one Z curve, okay? Now, I want to talk about p-value. So there's different ways to say the same thing or different ways to look at the same thing. But this is one way. All you need to do the statistical test is to know what Z star is and what Z is. And Z comes from your sample. And if you're doing means, okay, Z is X bar minus mu sub naught over the standard error. So this is your test statistic, and it's called a statistic because it comes from the sample. You have to know what your sample is to know what this Z is, and your sample is X bar. You get an average value of all those individuals that make up a single sample. That's X bar. M mu naught, you already know. You stated that in your null hypothesis. You already have this information. It's published that the population mean is supposed to be such and such. So you already know this. This standard error you get from your sample also, right? Standard error is equal to this standard deviation as, that's the standard deviation of the sample divided by the square root of n, which is the number of individual elements in the sample. So if I go out and I get 10 units of something that's in, and I get I can get their mean, which is X bar, and I can get the standard deviation of those 10 individual units, and that's S. So standard error, which I've said this a lot of times, but I want people to know it. Standard error is the standard deviation of the X bars, okay? So this S is the standard deviation of the X's, okay, of the individuals that make up an X bar. But if you were to sample over and over again, you'd get an X bar each time, right? You go get 10 and get their average. That's one sample. Go do that again, you get another one. And then you get another one. Well, standard error is just what the standard deviation of these means is. So you can look at this and say, this is like the standard deviations of these. So when you look at this is the distance from your sample to the proposed mean. That's just a distance, how far away from it is. And this top number is how far away it is in X, right? And the X scale, how many units apart this difference is. But then we divide that by how big is one standard error, or one standard deviation of X is how much. And this tells us that. This tells us what one standard deviation of X bar is. So this is a count. It's this distance from your sample to the proposed mean. It's this distance. And then you're saying, how many standard errors is this distance? When you divide by this is now a count of how many standard errors make up this distance. That's what Z is, Z score. So that's why we could put, the Z scale here, 0, +1, +2, +3, -1, -2. So these would be standard errors now, and that's called the sampling distribution. The distribution of the X bars is called sampling distribution. And this curve is intended to represent the distribution of the X bars. So these standard deviation units here are standard error units. And this tells us how big one standard error is. So that's the whole shebang there as far as the test. You're comparing the test statistic, which is a number that comes from your sample. You have to get a sample to get this. because that gives you X bar, and you determine this from your sample. Okay, that gives you this Z, which is a statistic. It came from the sample. We compare that to our threshold or trigger value, which is Z star, which has nothing to do with the sample. That just has to do with the confidence level for this curve. That sets where the flags are going to be on this curve, and it just depends on what confidence level you're testing at. Okay, and then the last thing I want to do, p-value, okay, which is what this whole thing started out with. But when you do a statistical test, p-value is reported. Okay, so let's say this was Z star, okay, and minus Z star. So when you write that, remember, you're talking about the point down here. You just draw the line to show this is, you're going to call, because this area is a probability under the curve. But so then we get a sample, and let's say our sample hit there, okay? So that's an X value. It's also a Z value, right? Because it's an X, whatever we're measuring the thing in, we get its X, and then we use this formula that we talked about. We get an X bar for the sample, and we plug it into this. That tells us what the Z value for that sample is, right? Okay, and so we have a Z value. So here's what p-value is. P-value is this probability. It's okay, but on a two-tailed test, we multiply this area times 2, okay? Because what you're saying is the probability of getting something this far away from the mean, or worse than that, probability of getting your sample value or a more extreme value is the p-value. And what do we mean by extreme? Means farther away from the mu sub naught. Or if you were doing proportions testing, this would be p naught from that mean value, or from z equals 0, okay? Because we know those are at the same place, right? Same place. Mu naught and z equals 0 are at the same place. Okay, so this area out here is the probability that a random sample would be out this far away from the mean, or worse than that, or even further. That's the p-value. But the two-tailed test says we don't know before we do the test where the sample is going to hit. So the p-value for a two-tailed test is the probability that you're going to get something that extreme, but it can be on either side. So whatever sample this z value is, well, this would be minus z, right? So it's I didn't draw that symmetrical, but this should look just like this does, excuse me, on the other side. So the p-value is the probability of getting a sample value or a more extreme value than your sample. Okay, so it's saying there's a very low probability. If this is true, there's a very low probability that I'll be at least this far away from the mean, okay? And then what we do is we compare the p-value with the significance level. If p is less than, or I think it might say equal, but that doesn't happen much. You just say less than. If p is less than the significance level, we reject the null. So there's two ways of doing the same thing. Do statistical test. If you know what z star and z are, you're done. You can reject or not reject just from looking at those two numbers. If this number is bigger than z star, you reject. So z bigger than z star, reject. Z less than z star, do not reject the null, okay? So you can do the test with just that, but you can also do the test with the p-value. If the p-value is less than the significance level, you reject. So what's that mean? Well, here's what the significance level is, okay? In this diagram here, the significance, I know this got too much written on it, but this, I don't know where I want to write it at. I got to significance level. The significance level is actually the whole area in the tail past z star. Area in tail beyond z star, okay? So the significance level would be, you start at z star and you get this total area here, okay? But actually in a two-tailed test, you have to say times 2 because it's this area plus this area from negative z star, okay? So both of these areas outside of z star and negative z star make up the significance level. So if the significance level equals 0.05, then this tail here, which is all this area from this line, okay, all the way back, that's the significance level, would be area in that tail would be 0.025, and the area in this tail would be area, which is the probability, is 0.025. So for the significance level of 0.05, that means you got 5% of your area. How can I do it? 5% of the area from this curve is outside of z star there. You can see it there. 5% is outside of, I'm trying to point, you know, these two, outside of these two thresholds, z star and negative z star. So there's a 5% chance you get a random sample. That sample lands beyond z star or less than negative z star. So that means there's a 2.5% chance that you'd be in either one of these tails, right? That you're each one individually. There's 2.5% probability, or 0.025, that you're less than negative z star in this tail, and a 0.025 chance that you're greater than positive Z star, okay? So back to this comparison, or you can see, if you can see all this at the same time. Can you see this? Let me see, almost. Yeah, okay. So we compare the p-value with the significance level. And that's what you're doing when you compare Z to Z star. Well, can't see that. When you compare Z to Z star, you're doing effectively the same thing as comparing this, this is 1/2 of the p-value, right? Because we got another half over here beyond where a sample would have been on the other side if it's the same distance from here, right? But so this is the p-value, half of it. You're comparing this p-value with this significance level. This is half the significance level from Z star out, and this is half of the p-value from Z out. So in a one-tailed test, it would be easier to see. You don't have the confusion of having two tails. So just pretend for a second that this is a one-tailed test, because this is the way it would be done. Your Z star number would be different if it's a one-tailed test, but you'll have a number for Z star that you still get from a table or compute if you're doing a one-tailed test. The difference is this whole area in a one-tailed test is 0.05. It's not 0.25 anymore. This whole area is 0.05. But say we were doing a one-tailed test, okay, you would still get Z star and Z and compare them. If the Z is bigger than Z star, you're going to reject the null, right? But that also says that this probability from Z on out is less than the probability from Z star all the way out, right? You see that? So this would be, if it's a one-tailed test, this would be your entire p-value. This would be your p-value, just what's in this tail from the sample out beyond the sample would be the p-value. The significance level is the probability from Z star all the way out. So you see here that the p-value is less than the significance level. So if this was a 0.05 significance level, this p-value here will be less than 0.05. It would be some numbers in here. It might be 0.03, right? And so a statistical test, when you're talking about p-values, is you compare your p-value that you get. Okay, the p-value comes from the sample. From the sample, that's where it comes from, right? You compare that with the significance level. And the significance level, it comes from, it is the Z star or the T star. And it just depends on your confidence level, what that value is. Well, the significance level is the probability. So when we're talking about 0.05 significance level, we're going to compare whatever we get in p-value with 0.05. If the p-value is less than 0.05, we reject, because we're saying the same thing as we're saying if we just compare the two Z's. We're saying for this value of this probability to be less than this probability, this point had to be on this side of that. Because if our sample was over here, let's say our sample had hit here, okay, then we would not reject the null because we're inside Z star. So our Z statistic that we'd calculate would be less than this, right? It's some Z score lower than this number, so we don't reject. But if you draw this and look at the probability in this tail from here all the way out, this probability is much bigger than the probability from Z star out. And the probability from Z star out is your significance level. So if our sample hit in here, our probability is going to be greater than this probability associated with the 0.05 significance level. It is 0.05. this probability is 0.05. If this is a one-tailed test, this probability is 0.05 at the 95% confidence level, 0.05 significance level. It means you have a 0.05 probability of hitting at Z star or more extreme than that, okay? If our sample hit in here, our probability from here, we have a bigger tail, right? We have all this area. So that's our p-value. This would be our p-value, and this whole tail would be the p-value if the sample hit here. So that p-value is going to be greater than 0.05. So that's the other thing. So it's two ways of doing the same thing. You can look at p-value, compare it to your significance level, and you know if you're going to reject or not. If your p, I should write value, if p-value is less than significance level, you reject the null. If the p-value is greater than the significance level, you do not reject. So two ways of doing the same thing, a test. All right, I've done a lot of talking. How about questions, Olivia? Any part of that that's not clear to you, or do you have a problem that you want to work on?
I am actually I'm on the last question on the extra credit.
Okay.
And I don't really know how to calculate the test statistics with that problem. Does that make sense?
Yeah. You're talking about on chi-square?
Yes.
Okay. Let me look it up here. I haven't actually done that one yet, so let me pull it up. Let me see. So if I say share screen, and let's go into I need to be in Chrome. I don't see Chrome down here. That's not good. I don't want to go into it with Safari because that causes trouble. Cannot minimize when you're recording. Okay, I'm gonna stop recording when I get to it. Maybe I can come back in and restart recording. Okay.
Okay.
So let me, or well, maybe I can do. Let's see. No, that is the desktop. Yeah, I stop recording.